We talked about the usage of matrices, usage of vectors, the real world problem to understand or to know why we should or why we are going to work in matrices and vectors. In this portion, we are trying to understand matrices more with their operations. So let us try to define the matrix first. So matrix is something, it's a arrangement of numbers in a tabular form. So uh, we have something like this. Uh, this is a matrix form. So which has m number of rows and n number of columns. So you can see each row is having the first subscript is increasing with the row and the second subscript is increasing with the column. So we have m number of rows and n number of columns, and that's why we say that it is a m cross n matrix. uh, so going ahead with this. Okay, so we have certain operations like matrix transpose, scalar multiplication and all. So either we will be going to talk a little later, and or else you can actually see in the see over the internet to understand what are these operations. Just to make sure of the notations, I'm just trying to discuss with the matrix addition. So if you look at the matrix addition, we actually do this addition component wise. So let's just try to see what does it mean by the component wise addition. So you take, let us say, the first row second column element 4, and you and another row, another matrix you also take again the first row second column element, and then you add them up to get the result, right? So 4 plus minus 5, which gives you minus 1, and that's how that you get in the uh, output of the addition, matrix addition. And that's what happened for each and every element. You take one element at from the same place, you take another element from B, this one, and then you put them in the product, this one, and that's how you get the addition of the matrices, right? So we, for this particular thing, for this addition, we need two matrices A and B, each of which should be of the same size, that is m rows and n columns. So whenever we say the size of a matrix, then it contains both the things, and the number of rows and the number of columns. So if we want to say that the size of two matrices is same, it means the number of rows should be same and the number of columns should also be same. So both things should be same. uh, the addition of the two matrices A and B can be defined in a compact notation as this one. So you see here, so what we are trying to do is that we say that C is equals to A plus B, then Cij, each element of the product or of the addition matrix, is given by the addition of respective elements of A and B. And that's how you get the addition of the two matrices. Now, looking for the matrix multiplication. So matrix multiplication is defined over two matrices, the size of which should be interesting in the sense that they should be of m cross n order and n cross k order. In the first matrix, the number of columns, and in the second matrix, the number of rows should be same. And then only you can multiply A and B. So the product size is m cross k, and it is defined in this format as a compact notation. So what we do, we sum over the number of rows, number of columns of A and the number of rows of B. You can see that here, if I enlarge it. So basically what we are doing, we are summing up it over L. L is the number of columns. It is representing each column of A and each row of B. So you are summing up over this L, and finally you getting a matrix of size M cross A, that is the rows of A and columns of B. So therefore, it is sometimes what happens that some multiplication or some matrix cannot be multiplied because of this idea of this nature of the definition of matrix multiplication. For example, this way you can see it has two columns but three rows in here and two columns of the first matrix, which does not match, and that's why they cannot be multiplied. So these are the few examples. These are the few examples which you can see for your understanding. So whether you have understood them or not, so you can see that. And then there is another example. This you can actually see this or notice that this particular matrix, this particular is one thing and this is another thing. Notice that this is the matrix, this is the same matrix as that this one, and this is the same matrix as that this one. But when you are doing A B, you are getting a 3 cross 3 matrix. When you are doing B A, you are getting 2 cross 2 matrix, right? So since you are getting a 2 cross 2 matrix and in one 3 cross 3 matrix, so you can safely say that AB is never been or may not be equals to BA. So they cannot be commutative. But interestingly, you should notice that you have just by one example you are saying that the matrix multiplication is not commutative. In what way or what is the reason to say that a particular thing is not that just by one example? In what cases we say that? So just to try to understand this particular idea, we are going or taking you to the definition of the commutative property. So we say that the something is commutative. A binary operation is commutative. Binary operation is commutative if and only if for every u1 and u2 in u1 o u2 should be equals to u2 o u1, right? So both the things should be equal. So if you want the definition of not commutative, you have to negate this statement. To okay, not this one, but little bit more. So from this part you have to negate. To negate that, we get, after negating that, we get there exists u1 and u2 in u such that u1 o u2 is not equals to u2 o u1, which means you just need to find out one particular pair of u1 and u2 in u such that u1 o u2 is not equals to u2 o u1. And that's why our job is done with just one example. Now we have certain special matrices called upper triangular matrix, lower triangular matrix, symmetric matrices, square matrices. You can again see it from the internet, so which will be easier to actually check it out. And the next part we will be discussing in the next video. Thank you.